Welcome back, children. In the previous videos, we talked about three types of materials as far as magnetism is concerned. We talked about the diamagnetic materials, the paramagnetic materials, and also the ferromagnetic materials. We said the diamagnetic materials are materials which are repelled by an external magnetic field, weakly though. Not very strongly, but there is a weak repulsion that you can see in the case of diamagnetic materials. And in the case of paramagnetic materials, there would be an attraction, but that would be again weak. So in the presence of an external magnetic field, a paramagnetic material can be attracted towards it, but slightly, not much. And then there are ferromagnetic materials which can become magnets on their own. There will be a strong attraction of the ferromagnetic materials when they are placed in an external magnetic field, and they themselves can become magnets. So these are three types of materials. When I say this, these materials are not in addition to the already existing materials. Any material that you see around you can be put in one of these three categories. For example, if I take iron, it is a ferromagnetic material and can become a magnet too. And iron is also a conductor. So if I take iron, I can put it in these two classifications. I can classify iron as a conductor and also as a ferromagnetic material. And if I take aluminum, for example, aluminum is a conductor and also a paramagnetic material. And if I take copper, it's a conductor and also a diamagnetic material. And if I take water, the pure water, it's an insulator. The pure water is an insulator. And it is also a diamagnetic thing. So, this is not something extra. What I mean by that is, there are not conductors, insulators, and diamagnetic materials. A substance can be a conductor and also a diamagnetic material. I want you to understand this. This grouping will not have any material which are not there in your earlier classification as far as conductivity was concerned. So whatever you had in that grouping, like conductors, insulators, and semiconductors, the same materials can be put in these categories. So these are not something extra. So I want you to understand that. Okay. Having said that, let's move on to talk about what causes this difference in magnetic behavior. Why are some materials diamagnetic materials and some other materials are paramagnetic materials and yet other materials are ferromagnetic materials? To understand that, we need to talk about what happens in an atom. We'll do it now.
You might not think of water as being magnetic, but it is, and so are graphite, aluminum, and glass. This is a new and different category of magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron, or nickel, or cobalt, becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet. And so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen which sticks to the magnet. I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnetic field. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a grown crystal of flat carbon layers which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present when they're chilled. They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic fields. One way to check whether an object is diamagnetic or paramagnetic is to see how it aligns itself in a magnetic field. Diamagnetic objects like glass will rotate to avoid magnets. Here, we see that the glass is diamagnetic because it twists to get to the weaker magnetic field. But aluminum rotates into the field, typical of a paramagnet. On the periodic table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamagnet? You have to know what the electrons are doing. Consider, for example, aluminum. We see from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p. Now it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that is free to be magnetized and attracted by the magnet. But what about a diamagnet like water? Yes, the water molecule. It has all of its electrons paired. It will not be magnetized. In fact, water is repelled by a magnetic field. The electrons come to lower energy as they are moved away from the magnet. In conclusion, when something is a paramagnet or a diamagnet, it tells you what its electrons are doing. In the case of a paramagnet, it has at least 1 unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
We know that each atom has a nucleus and electrons orbiting around that nucleus. We also know that each orbit will have its own orbitals. And in each orbital you can have electrons. And sometimes they are paired and sometimes they are not paired. The paired electrons will be moving in opposite directions. That also we know. So, we are going to see what happens when you take an atom and place one of its electrons in the presence of an external magnetic field. Okay. Here, I have an electron orbiting around the nucleus. So, this is electron, this is the nucleus, this is orbiting around the nucleus. And I have kept this electron, this arrangement, in an external magnetic field. So what I mean by that is, if this is the atom, then I am bringing a magnet close to it. Okay, so then what's going to happen? I've kept this magnet here, so this is north, then the field lines are going like this. So now the electron, right, is kept inside the field of this magnet. So what do you expect to happen here? Well, electron is orbiting the nucleus. So if the electron is orbiting the nucleus in this direction, which is actually the counterclockwise direction, then I can assume that the current travels in the clockwise direction. Okay, so now I have current in the presence of an external magnetic field, so I can expect a force to act on the electron. Electron is a moving charge kept in the presence of an external magnetic field. So it's going around the nucleus, which means an additional thing, which means that this is a magnetic dipole. This electron itself is a magnetic dipole. So the electron will also have a magnetic dipole moment. And what is that? And that we said is M of this electron, the magnetic dipole moment, is equal to NIA. N is the number of turns, and then I is the current flowing in the loops, and A is the area covered by the loop. In this case, there is only one turn, see, only one loop, it keeps going in that loop. Okay, so N is 1, let me take it as I, and then A is the area covered by this loop. Okay, so this is I. Then what would be the direction of this magnetic dipole moment? And we said that if I assume the current to go in like this, then the magnetic dipole moment using the right hand rule then would be down. So the current is going like that, so the magnetic dipole moment is down. So I'll say that M in this case is down. Okay, so maybe I'll do it somewhere else. So you know that M is down. If we take this electron, for example, we take another electron which is going around the same nucleus, but notice that it is going in the opposite direction. Now this electron is going in the clockwise direction. Let us suppose it is a paired electrons. So one electron is moving in this direction and the other electron is moving in the opposite direction. So in that case, the current can be assumed to flow in this direction, in the anti-clockwise direction. So if the current is going to flow in that direction, what would be the magnetic dipole moment of this electron? Well, let's make me look. So it's a dipole now. So this is going to be M is equal to N again is 1 and I would be the same as the previous electron, and A will be the same, but then this time the direction would be up. So this is the direction of the magnetic dipole moment. Okay. Fine. But would it have a net magnetic dipole moment, the paired electrons? No, the pair would not have a net dipole moment, because this dipole moment of one electron will be cancelled by the dipole moment of the other electron. So the pair as a whole will not have a net magnetic dipole moment. We want you to remember this. Second, we will talk about the force experienced by them. So the direction of the current is this way. If we take this electron, so it goes like this. Okay. Now let me take the force experienced with this electron when it is here. It goes like that, but then the current is in the opposite direction. So the electron is going that way, the current is in the opposite direction. And let us say that at this point, B is in this direction. Then what do you think is going to be the direction of the force experienced by it? So this is the direction of B at this point, and I is actually coming towards you. Actually, electron is going in this direction, into the board, but the current can be assumed to be coming out of the board. So it's like this. So the current is coming out, and B slightly angled this way. So you can notice that ITL cross B for that would be in this direction. The force experienced with the electron would be in this direction. So let me draw it here. Let me say that the current is coming towards you when the electron is at this position. Current is coming towards you, and the magnetic field this is your B external. So the force is said will be this direction. The force will be in this direction. This will be the force. So you can see that when the electron is here, it experiences a force in this direction. And what happens when the electron comes here, which means that the current is going into the board, the same stuff. Now the current is going into the board, then B is in this direction now. B external is in this direction. Now you can see that here current is going into the board, B is in this direction. So now IDL cross B will give me the force in this direction. So notice that the force when it is here is going to be in this direction. Okay. I don't have it. Okay. So in this direction. So when the electron goes in a loop, at every point it's going to experience a force, and it is directed in different directions. But then you can see that on the average, these forces, like the horizontal components of these forces, can be cancelled. On the average, in the horizontal direction, the electron will not experience any force. But in the vertical direction, there would be a force at every point. What I mean by that is, if I take this force and if I get the two components of this force, the horizontal and then the vertical components of this force, then you see at every point the horizontal components will cancel, but the vertical components will remain. So this electron will experience a net upward force. Okay, so the force on this is going to be upward. This electron. I can use the same logic for this electron, which is going in the opposite direction, and if you do it, you will know that this electron will be experiencing a downward force, like that. Okay? This electron will be experiencing a downward force. So if the magnetic field is constant, I value of this electron is the same as the I value of the other electron, because they are paired, the paired electrons are what we're talking about. Now they're paired. So this electron will experience an upward force, and this electron will experience the downward force. So the net force on the pair is also 0, even if you keep it in an external magnetic field. So you keep the electrons in an external magnetic field, the net force on the pair is 0. The net magnetic moment of that pair is also 0. But if there is an unpaired electron, then the situation is different. Then you will get only one electron, and that electron will experience a net upward force. I want you to understand this first. Now, this is about constant external magnetic field. What about a varying magnetic field? What do you mean by that? For example, I take this magnet, okay? Now this is the electron. What I mean by varying magnetic field is that when I bring this magnet from here to the position, like this, the atom is here, I am bringing it here. Then what happens? When it is at this distance, the magnet is at this distance, this atom, the magnetic field at this point will have one value. But as I bring it closer, then it will have another value. When I bring it even closer, it will have even bigger value, the magnetic field strength. So as I bring it nearer and nearer, then what happens is that the magnetic field at that point is changing. Well, if the magnetic field is changing, then what do you expect to happen? We expect an EMF to be induced from Faraday's law, which you studied in your 10th standard. We will talk about Faraday's law and Lenz's law in the next lesson in much more detail, but then I just want you to recollect what you studied in your 10th standard about magnetic induction. So the varying magnetic field, when the magnetic field changes, then that will create an electric field. So when I bring a magnet here, I bring a magnet from this position to this position near an atom, then what happens is that it induces an electric field to be generated. A varying magnetic field will produce an electric field. So in which direction would it be? Well, from Faraday's and Lenz's law, we know that the induced EMF should oppose the magnetic field. Okay, it should. Though, what do you mean by that? So the magnetic field, as I bring the magnet from here to there, then it is the magnetic field lines are becoming more and more. So the magnetic field strength is increased. So the induced EMF would send the current in such a way that the current would create its own magnetic field that will oppose this increase in the field, the external field. We'll talk about it later in the next lesson, but I just want you to understand this. I want you to understand that because this is increasing, then this should be reduced. So if this has to be reduced, then the current must be flowing in this direction. Okay, so it must be flowing in this direction. So this puts magnetic flux, more flux in this direction. So it opposes the magnetic, the change in the magnetic field. Anyway, so what it means is that the current in this direction will increase. That's what I'm trying to say. How you will get to know in detail in the next lesson. I just want you to remember this. When I bring an external magnetic field near an electron, then if the field is changing, since the field is changing, then the current in this the loop will increase if the dipole moment of the electron is downwards. Just keep that in mind. That's all you need to know now. We'll explain why the next lesson. So if you bring it here, the field is in this direction, but notice that the dipole moment of this electron is opposite direction. So if the field is increasing, now this current will increase, which means that there is only one electron. So the electron will accelerate, will speed up. So remember that the dipole moment, which is in the direction opposite to the external field, will make the electron go faster. Or I should say, the electron that has a dipole moment, which is opposing the external magnetic field, will accelerate when the field strength is increasing. The external field strength is increasing. As I bring it here, this electron will start moving faster. Then what happens? So then what will happen now? If the electron is moving faster, then I increases. So what will happen now? The force will also increase. The force experienced by this electron will also increase. So this will be like that. So this will be the new force. This will be the new force. The force increases as I bring the magnet from here to here. And what will happen here? Clearly, this will slow down this electron. Why is also the same reason. As I bring the magnet from here near this electron, then the field increases, then the EMF will try to put the current in this direction, as it was trying to do it here. It will try to put the current in this direction, but this electronic current is in this direction, so this electron will slow down because this is in opposition. The direction in which the magnet tries to put the current is in opposition to the direction of the electronic current. So clearly, the electron will slow down. So this force now, the force, if the electron is slowing down, the current will be less. If the current is less, then the force experienced by it will also be less. So I'll have a smaller force. So notice here. Now what happens to this pair? So previously, in a constant magnetic field, the pair did not experience a net force. But in a varying magnetic field, then what happens here is that the pair is going to experience a net force because the force on this electron is higher than the force on this electron. So there will be a net force on the pair. So as I bring the magnet close to a pair of electrons in an atom, then they experience a net force in which direction? Notice it's going away from the magnet. Because they experience a net force and they go like that. As I bring it here, and they go like that. So this happens in all the atoms, even if it is iron, a ferromagnetic material. This should happen. Every paired electron, every pair of electrons in an orbital will experience diamagnetism. So when you bring a magnet near it, that pair would try to go away from it. So almost all elements have pairs of electrons, and all pairs will experience this. So this diamagnetism, getting repelled by a magnet, is present in every material including iron. But what happens? Then why do you get paramagnetic materials and also ferromagnetic materials? And that is because you have unpaired electrons. They will experience a different type of force, and all these then there will be a net force on the materials, because sometimes those unpaired electronic effect will take over. It can be greater than this paired electronic effect. So they can get, weakly attracted towards a magnet. And it is not just these electrons. The net magnetic moment of an electron, of an atom, depends on the sum of the magnetic moments of all the individual electrons in that atom. And if you take a material, then the magnetic moments of that material depends on the individual magnetic moments of all the atoms that make up that material. So how they are oriented, in which way they are, in which direction they are, and that will decide what the final magnetic moment is. But I want you to understand this. Every element, everything is diamagnetic in one sense or the other. They go away from the magnet. But then, in some materials, the electronic configuration can overrule this diamagnetic nature of all materials, and then they become paramagnetic. And if they can be paramagnetic, then they can also become ferromagnetic a little later. We'll talk about it later. But I want you to understand this. So, if you look at the magnetic field lines of a material, like for example, like I have a diamagnetic material. Okay, so I have a diamagnetic material like this. This is a diamagnetic material. So if I have an external magnetic field, then the field lines around that material will be like this. So it will go like that. Okay, it's kind of, you can see that they come, they don't, then as they come here, then kind of repelled. So that is, it will show some kind of a repulsion. There is no attraction that will be taking place in the case of a diamagnetic material. If you take superconductors, conductors are perfect diamagnetic materials. They repel the external magnetic field lines completely. There is nothing that goes in. Notice here, I've just taken one, a non-superconductor diamagnetic material, and I have diamagnetic material which is available, like copper. If I have copper like this, then there will be some field lines inside, but it is not exactly perfect. In the sense, like some magnetism can go. There is repulsion, you can see, but then it's not fully. It's not repelling everything. But if you take a superconductor, no line will go through this. All lines will bypass the superconductor. So that is used in magnetic levitation and all that. So like superconductors are used for super fast trains and stuff. Okay, so that is an advantage of that. So superconductors are perfect diamagnetic materials. But the materials where this pairing takes over, okay, everything else. They become diamagnetic materials. It doesn't have to happen only at the atomic level, like at the molecular level too. If there are two things come together, and then there could be this pairing effect can take place, and the material can become diamagnetic. So you can consider a diamagnetic material as a net paired electron material. The electrons may be paired at the atomic level, or at the molecular level, or at the material level. You have a set of paired electrons, and the net dipole moment would be 0, but then when you bring the material in the presence of an external magnetic field, then the material is going to be weakly repelled by the external magnetic field, as we just saw. That is about the diamagnetic materials. But what about the paramagnetic materials? The paramagnetic materials, there would be a net magnetic moment. It's like an unpaired electron. You'll have one or more unpaired electrons in an atom, either at the atomic level, or at the molecular level, or the material level, that you will have. It's equivalent to having unpaired electrons. Okay, but even though each atom may have a net magnetic moment, meaning a net unpaired electron, because of the temperature, because of the thermal agitation that is taking place inside that material, and then the magnetic dipole moments may not be oriented in such a way that you get a net magnetic moment for the material as a whole. Each atom may have it, but then because of temperature, your normal temperature, low temperature, high temperature, that all the atoms are like, so they are moving. So because of that, the alignment of the dipole moment may not result in a net dipole moment for the material. But then, when you take this material, which doesn't exhibit a net dipole moment in normal temperatures, and bring this material in the presence of an external magnetic field, then you can see that the atoms try to align their dipole moments with that of the external magnetic field. So there is some kind of a magnetization that is taking place when you have a paramagnetic material in the presence of an external magnetic field. So you can say that the magnetization, okay, because the magnetic dipole moments of the atoms are getting aligned in the presence of an external magnetic field. So the magnetization, you can say in this case, is expectedly proportional to the strength of the field. So B0 is a field, then the B0 is increasing, then the magnetization will also increase. More and more atoms will align with this magnetic field. But then, if the temperature is more, then the atoms will be chaotic, right? They will be moving, they'll try to move in different directions now. Because that's the reason why you even have the temperature. The electrons will have to excite and then come back in that process, they have to radiate energy. So the more the energy, then more the excitation, and then coming back, and all, the temperature will be more. And because of this, you may not have a net magnetic moment, right? So if the temperature is more, then the magnetization could be less for the same external magnetic field. At 20 degrees Celsius, B0 can make a paramagnetic material magnetized to a certain extent. But at 40 degrees Celsius, the same B0, the same magnetic field strength, would be able to magnetize it only a little, less than what it was able to do it at a lower temperature. Because now the atoms are more chaotic, so bringing them to align the magnetic field is a little difficult. So I can say that the magnetization is inversely proportional to the temperature. So the magnetization is directly proportional to the applied magnetic field, the external magnetic field, and inversely proportional to the temperature of the material. So if I combine these two, then I have this expression M is equal to C B naught by T. In this case, C is called as Curie constant. Because Pierre Curie was a person who did a lot of research on this, and we are calling this as the Curie constant, C. And we also know that magnetization is equal to this Xi is permeability, and then H is a magnetic field intensity from our previous discussions. So if I'm going to use this, then Xi H is equal to C, to instead of B naught, I'm going to get mu naught H, so divided by T. So H and H will cancel, so we'll get Xi is equal to C mu naught by T. So you know that Xi is the permeability of the material. But notice now that permeability now just does not depend on the material alone, it also depends on the temperature at which the material is. So as the temperature increases, the permeability reduces. It is difficult to magnetize the material. So this is called as Curie's law. In a paramagnetic material, the magnetization is proportional to the applied magnetic field V naught and inversely proportional to the temperature at which the paramagnetic material is. This is called as the Curie's law. So as you increase the magnetic field strength B naught, keeping the material at a particular temperature, then what happens is that the material is getting magnetized more and more, meaning that more and more atoms are aligning their dipole moments with the applied field. So I keep increasing B naught from 0 to some value. So then more and more atoms are getting aligned to the applied external field, but at some point all the atoms in that material would have got aligned with the applied magnetic field. So after that, even if you increase the magnetic field strength, the magnetization will not increase because all the atoms are now aligned. So increasing the magnetic field will not make any more alignment because everything in that material is aligned to the applied magnetic field. So that magnetization is called as MS. This is the magnetization at saturation. So you have saturated the magnetization because every atom in that material is now aligned to the applied magnetic field. So suppose there are n atoms in that material and m being the magnetic dipole moment of each of that atom, then magnetization would be Nm by V, the volume of the material. We saw that before. We said like the magnetization is the total magnetic moment of the material divided by the volume of that material. So at saturation, the magnetization value ms would be equal to N by V. And the moment you remove the magnetic field, then what happens to this magnetization? They will go back to being chaotic again. Why? Because there's temperature. At that temperature, they're chaotic. And you have aligned them with this B naught. So they were magnetized. So the moment you remove B naught, then temperature will take over. The material would not be magnetic again. So that is why you call this as a paramagnet. It's not magnet at all times. After you have magnetized it, it won't remain a magnet. It won't be a permanent magnet. So the moment you remove the magnetic field, then it will go back to being a non-magnet. Because the temperature effect will take over and this will become a non-magnet again. As long as you keep it in an external field, then that will get attracted to the field slightly. Why does it attract slightly? Because of temperature again. Because a particular strength may not be able to make this, may not be able to make all the atoms in that material to align. Only a few will align. So the net magnetic moment will be small, so the attraction will be small. So as you keep increasing the magnetic field value, then the attraction will become more and more and more. Then at saturation, then you will get the maximum attraction. And beyond saturation, even if you increase the magnetic field value, nothing else is going to happen because all the atoms are aligned. And you remove it, you remove the external magnet, then it will no longer be a magnet again. So the temperature effect will take over, then the atoms will stop moving in different directions. Hope this is clear to you. So now let's talk about what happens when you bring a magnet near a paramagnetic material. So what will happen to the field lines? The field lines would look something like this. Because these are the external magnetic field lines, then now we go into the paramagnetic material. Now that wasn't the case with a diamagnetic material which we saw before. Because in that case, the lines were repelled. They were going over the material, now they go into the material. Hope you understand this.